probability of x and z. Phi is approximate posterior Q of z. And the expectation is under this approximate posterior Q of z. And then plus the Q of divergence between the approximate posterior and the true posterior, right? So as we illustrated before, since ideally we want to directly minimize the K-L divergence between your approximate distribution and your true posterior distribution, however, it's kind of infeasible, right? If I can do that directly, why would I bother to compute the approximation? I can directly compute the true posterior, right? So we have to detour, right? The detour is based on this decomposition because the law of marginal probability is fixed. So minimizing this K-L family. So in the last lecture, we introduced a set of factorized family we call mean field family, where each group represents a subvector, so Z1 to Zn. So the mean field direction posterior assumes that your approximate posterior is factorized over posterior over this m subvectors. So it's Q of Zi. So each Q of Zi is an independent approximate posterior distribution. Basically, it assumes that okay, in my approximate posterior family, I assume okay, Z1, Z2 to Zm are independent to each other, which is obviously incorrect. It's not correct in most cases, but just using this can in practically often gives us like quite accurate approximation. Let's see, we can then to maximize this variational multi-evidence lower bound in the mean field family, we can do the alternative update. Each time I pick up one approximate posterior, say QZI, and fix all the other QZJs, right, to update QZI. So I'm showing that the product of the approximate posteriors of all the other ZJs other than ZI. Right? So, right? So if you take the expectation under, say, QZ1 to QZI minus 1, QZI plus 1 to QZM, right? You do the expectation, you integrate out or you marginalize out all the other random variables other than Zi, right? So then after this expectation, you are leaving only one random variable, Zi, right? So it's actually a function of Zi. And now you just take exponential and normalize it. It is your updated approximate posterior for QZI. Right? And then next you fix QZI, you switch to say QZI plus 1 and do the same thing. Right? You cyclically update each QZ1, QZ2 until QZM. You finish one iteration. And then you do many iterations until so no difference between those QZI update after updates, right? Or maximum number of iterations have been finished. That's the idea. And every time when you update one single Q of Zi, to ensure that your variational multi-evidence lower bound is increased. And we haven't shown you that. Why? If you still remember. By the way, if you do not have impression, doesn't matter because in your homework you have to rederive them again because you have to implement those kind of things. So that's mainly about like global version inference. Oh, another thing is that if you do not choose like factorized form like mean field family, you can choose other. You can set QZ to be some Gaussian distribution. Totally valid. And then the remaining question is like, how do I determine the mean and covariance of the Gaussian, right? So the problem because like I want to maximize this lower bound with respect to some posterior mean and the variance. Then you just calculate gradient and throw it into LBFTS or whatever optimization algorithm. Just maximize this. It's just an ordinary optimization problem. Then I can construct a lower bound of PMF. xi theta is substitute P of xi given theta by its lower bound, I construct a lower bound of the whole general probability. So this is the idea. And which inequality is most often used to construct such bound? That reduces to the convex conjugate we have discussed before, right? So linear form. So now you see, after replacing this form, introduce an extra parameter lambda. But the terms which is relevant to x is only a linear term, lambda x. Right? So g of lambda is has nothing to do with it. It involves a linear term here. And then we can, like, for example, update anything regarding x. And then we alternative update lambda. G lambda usually has some kind of form, and then we can do some optimization or whatever on that. So this is the key idea. Because if you use this convex conjugate, you essentially introduce a linear bound in terms of the original variables. So usually, if you introduce some linear form into that, your difficulty will be much reduced. So this law of general probability is usually decomposed as log square plus the summation of the log likelihood on each individual training example. So typically, if I can find that this individual log likelihood is convex to, say, the model parameter theta, right? And then I introduce this convex conjugate, namely lower bound, and then replace this log likelihood by this lower bound. So now you see, inside this lower bound, we only have a linear term regarding the theta, right? And now you combine the theta and the theta in the log prior, you do the estimation, you do the variational posterior estimation, whatever. It will be much easier. Does it make sense? Any questions so far? Does this high-level idea make sense? Okay, assume everyone. Now we'll look at the specific example. We're going to use this approach to do the variational logistic regression. So I want you to be careful because this example is pretty complicated. That being said, if you can go through the details of this example, it will be much easier for you to deal with any other cases. So I will leave all the details of derivation in the website. I will show that, but I will recommend you to follow those details afterwards. Anyway, you will be required to implement this variational logistic regression. So as we mentioned, it is difficult to compute the posterior distribution of all the parameters in the logistic regression model, right? Because we have the prior usually to be a Gaussian distribution. The likelihood is Bernoulli likelihood determined by the sigma function. So if I write it down, it will be something like this. Right? It goes through n training examples, or in each training example, the likelihood will be the sigmoid of the W transpose, our feature vector to the power of the label times 1 minus the sigmoid to the power of 1 minus the I. So this is Gaussian and this is sigmoid. This is really hard to combine them together to do the integration, all kinds of stuff, right? So naturally, we'd like to see whether if I take a log likelihood over those sigmoid function, can I use the convex conjugate to get a lower bound, right? The lower bound then becomes some linear form, and it will be much easier when you combine with a Gaussian term. But unfortunately, if you take a logarithm of the sigmoid, you cannot use the lower bound we just mentioned before. Right? You can use upper bound, but usually we won't like upper bound. We won't like enlarge the model evidence, then maximize upper bound. It's very likely that you maximize your upper bound, but your model evidence doesn't change. So then how can we address this issue? Right? How can we properly introduce the convex conjugate here? Right? So that comes a very classical trick. So if you take logarithm of the sigmoid, it will look like this: minus logarithm 1 plus e2 minus x. But if we take out a common factor in log term, which is e to the minus half x, so you have this e to the half x plus e to the minus half x. And log product is a summation of log, right? So you can move this term outside. You have a half x because you have a minus sign here, right? You have half x subtracted by logarithm of e to the half x plus e to the minus half x. So we can just put this linear term aside because it doesn't matter. Convex function, linear function is all of e to the half of x plus e to the minus half of x. Obviously, it's not convex. So, but we found some interesting property for this function. Is that first, this function is and also fx is equal to f of the absolute value of x. If x is bigger than 0, then this term are corresponding to each other, right? If x is less than 0, then this one corresponds to this, and this one corresponds to like that, right? So the key observation is that so those guys who find this it's really smart. The other guy is so now is minus log e to the meaning that your second order derivative is of this h function is positive. Then this h function is convex. H function is actually the function f in terms of t squared, right? So see, it's kind of to me it's kind of I don't know how they discover it because it's really not very obvious. So see, this one is definitely not convex. You cannot prove that. And how can they guess that what if I will as a function of x? It's not trivial. You have to do quite a amount of work. X conjugate, it will have a lower bound in terms of x squared. So don't confuse here. So you have a lambda x squared subtracted by some g lambda, right? G lambda, remember, g lambda is negative intercept of it. So g of lambda is maximum value of lambda x squared subtracted by this constant. So now let us look at how we obtain g of lambda, right? So lambda is the gradient x squared. So here, if you take the gradient, instead of 0, you have a lambda. So remember, because this is linear to x squared, right? You take the gradient with respect to x squared, you have lambda subtracted by. So again, to calculate the gradient of this f with respect to x squared, you can first take the gradient with respect to x, and then take the gradient, dx over dx squared. Right? The exactly same trick we just mentioned. So we can go back to say this is actually the gradient. Because we have essentially derived this gradient, which is here. So we can just copy here. We don't need to derive again, right? So and here we use one observation that the tan h function is e to the power of x subtracted e to the minus x divided by the summation. So you can see here, it is tan h, right? The input is just the half of x, right? So that's why we can write it when we solve this infinity, we can write it as lambda plus 1 over 4x tan h half of x, right? So 4x is here. 1 over 4, 1 over x. 1 over x is here, right? And this is tan h of x. So if you just put them together, you have this. So tan h, your optimal x is just Psi. Also, I don't know Psi, what is Psi, right? It's just there's some value Psi here. Right? And then I'm now gonna represent Psi in terms of lambda. Instead, I do the reverse. I represent lambda in terms of Psi. Although lambda is some kind of given value, right? That being said, like given this optimal value of Psi, lambda is essentially equals to this minus 1 over 4 of Psi tan h half Psi. Right? And you can further simplify it by represent lambda Psi in terms of the sigmoid function of Psi, right? Because this is pretty straightforward because these are all about like e to the x minus e to the x terms. It's very easy to go back. So suppose we have this optimal value of x, which corresponds to lambda Psi, right? We can represent lambda in terms of this Psi. But as for now, don't feel like uncomfortable on that. This is just different type of representation. Like ideally, we want to solve x in terms of lambda, so I got a function of g lambda which also represented in terms of lambda, right? But now we find it's too difficult, right? So now I would like to introduce another. Just assume like I know the optimal value of Psi, right? G of lambda will be this bond evaluated at the optimal value of x squared Psi, right? So it will be lambda Psi squared subtracted by Psi. So if you just substitute the form of f Psi by f Psi by f, you end up with this. Any questions so far? Is everybody comfortable? Or is fine? So we'll continue, right? So now we have again, I mean this form is by the optimal value of x squared. That's it. So it's still a linear form. The only issue is that we do not know Psi. But it doesn't matter because later we'll replace lambda by Psi in a bond, then